It's a great pleasure to introduce Jeff Stife. And I would like to start by saying that he's the Birnbaum lecturer this year. So every year we have one distinguished mathematician, probabilist, give Birnbaum lecture. Let me say a few words about William Birnbaum. Some of you know who he was, but some of you may be attending this conference for the first time. William Birnbaum lived almost the whole 20th century, from 1903 to 2000. It gives me a special pleasure to say a few words about him because he was born in Poland. And he got his PhD in Lwów, which was in Poland before the war, and that's the place where much of pre-war Polish mathematics was done. Some of the best-known names associated with Lwów were Banach, Ulam, Katz, and Birnbaum. Well, I will not go into detailed history, but in 1939, he came to the University of Washington, and he stayed at the University of Washington until the end of his life. Of course, at the end, he was retired. He's probably best known as a statistician. He was one of the editors of the Annals of Mathematical Statistics. This was the journal that preceded separate journals of Annals of Statistics and Annals of Probability. He was also the president of the IMS. But he also made a very important contribution to mathematics. Nowadays, many people know about Orlich spaces, but some people started calling them Birnbaum Orlich spaces because Birnbaum and Orlich co-authored the first original paper, and Orlich kept working on these spaces, and Birnbaum moved to different problems. And he made mostly his contributions to statistics. Anyhow, so it's a great pleasure to have a distinguished speaker today, and who will talk about Boolean functions, noise sensitivity, influences, and percolation.
Oh, thanks a lot, Chris. So first I want to thank the organizers for inviting me to give this talk. I'm visiting here at Microsoft for a year and having great pleasure, enjoying myself talking to the theory group and all the visitors, and it's a great opportunity. I appreciate being here. So I'm going to talk about the following topics. It's going to be very much of an overview lecture. So feel free to interrupt me anytime you want with comments or questions. So these are the four concepts I'll be discussing: Boolean functions, noise sensitivity, influences, and how they arise in a particular model called percolation. And I think Asaf said all his pictures were due to someone else, so these pictures also borrowed from elsewhere. Okay, so there's some lecture notes that Christophe Garbon and I wrote called Noise Sensitivity of Boolean Functions in Percolation. And they're already published, but we're in the process of putting them, extending them, and writing a book. So if anyone were to look at the lecture notes and have any comments, we'd be we'd welcome any types of comments for the coming book. And today's lecture will be a brief survey of some of the topics covered in these lecture notes. Okay, so the first thing we're going to talk about are Boolean functions and noise sensitivity. And the basic setup for noise sensitivity is quite elementary. We have n random variables, x1 through xn. They're IID plus or minus 1, each with probability a half. So we just have n coin flips. And we denote the vector by x. And then we have a function f from minus 1, 1 to the n. This is sequences of length n of plus and minus 1s. Sequence length n of plus and minus 1s into plus or minus 1. And this is called the Boolean function. It just has two possible outputs. And so in some sense, this function will be the function will be a function of these n inputs, x1 through xn. So this is what a Boolean function is. And the next notion we need to do to introduce noise sensitivity is we have to talk about a small perturbation of x. So x is denoted there, And x epsilon is here, and this this is again a vector of length n, x1 epsilon through xn epsilon, which we think of as a small perturbation of x. And the way it's going to be perturbed, and it's a very simple way, you go to each of these n bits, and independently, with probability epsilon, I take that bit, and I throw it away, and I replace it by a new plus or minus 1, each with probability a half, completely independently. So for each of these is erased with probability, a very small probability epsilon, and replaced by a new coin flip. So that's our perturbation. And then the basic question is, if we look at, and of course note that x epsilon, this perturbed thing, is also, of course, because everything is independent and symmetric, this is again a sequence of n coin flips. They're all, it's still IID a half a half. And the basic question of noise sensitivity is, if we look at f of x in f of x epsilon, of f of the small perturbation, are these things going to be close to independent, or are they going to be highly correlated? Now, obviously, if epsilon is extremely small, then x epsilon and x will be the same with very high probability. You wouldn't have perturbed it. And these f of x and f of x epsilon will be more or less the same value, almost with probability close to 1. And so we have it highly correlated. So what we should think instead is epsilon is very small but fixed. And this function f will be a function of very many variables and some complicated function of these n variables. And then it's not quite clear if things will be independent or not. And this is the first definition. This is a definition by Benjamini, Kalai, and Shrum, who introduced this concept. We say a sequence of Boolean functions, fn, which will be mapping as above sequences of length n into plus or minus 1. We call it noise sensitive if you take any fixed epsilon bigger than 0, and we look at the correlation of the covariance between fn of x and fn of x epsilon. This is the covariance that this goes to 0. Now, what this means, fn is just taking two values. So being uncorrelated is the same as being independent. So this simply says that if we look at f of x and f of x epsilon, these are asymptotically independent. They become independent as n goes to infinity if epsilon is fixed. OK, so as I said, interrupt me if there are any comments or questions. OK, so let's take 3 quick examples that are easy. The first one is the simplest Boolean function in the world. It's called the dictator function. Fn of x1 through xn is simply x1. It's just the first bit. So this, of course, doesn't really depend upon n. And it's not so hard to see. If you do a small perturbation of this, most likely things are not going to change. And this will not be noise sensitive. Because the function doesn't really even depend upon n. An example of a noise-sensitive function is the parity function. These bits are plus or minus 1, so I can multiply them out. And if I take the product of them, we call this the parity function. This one is another Boolean function. It turns out it is noise-sensitive, because basically, if epsilon's fixed and n is enormously big, with very high probability, you'll be resampling one of the bits with very large probability. And once it's resampled, it's just as likely to be plus or minus 1. Just as likely to be plus or minus 1. And so the things become completely uncorrelated and independent. An example where things are maybe not so clear at first is something which is called the majority function. So in this function, n, the number of variables has to be odd. And what the function simply does, it looks at the n bits, and it looks if there's a majority of 1 or a majority of minus 1s. If it's a majority of 1s, the function outputs 1. If it's a majority of minus 1s, it outputs minus 1. One way to do that is you can just sum up the bits. They're plus or minus 1, and you take the sign of the sum. So this gives you the majority function. And the question is whether this is noise sensitive or not is not as perhaps obvious as the other ones, but it turns out this one is not noise sensitive. So if you fix your epsilon very small, imagine an election with Democrats and Republicans, and with everything being IID a half, and you take and you see that the Democrats won, and then you change a very small percentage of the people's votes, the Democrats will still be the winners. So this is not noise sensitive. OK. So our main example of interest, that'll be of interest to the talk, is percolation theory. So in percolation theory, what we do is we have an R by R square, a piece of the hexagonal lattice, exactly like this. And each of those hexagons is painted black or white, each with probability 1/2 independently. And I think of those as my input bits. They're now I have about R, since it's R by R, I have about R squared of these plus or minus 1. Think of black as 1 and white as -1. And now if I can define a Boolean function which describes the percolation picture. What I'm going to do is I'm going to ask if there's a crossing from the left side to the right consisting only of black hexagons. So in this particular realization, there is a black path from the left to the right side going, as I just showed you, the probability of this is about 1/2. And so we define a Boolean function, 1 if there's a left to right black crossing, and -1 if it's not. So this function simply tells you if there's this right crossing. And you can ask if this is noise sensitive. Are percolation crossings noise sensitive? So the way you think about this is on the left side, we have our original percolation configuration, omega. And let's assume that there is a left to 1. I've made black, turned it into red. Let's assume there is a left to right crossing. And now I'm going to apply this so-called epsilon noise. So each of these only epsilon portion of these hexagons are going to be reflipped to determine their value. And the question is there still a crossing from left to right? Given the fact there was a crossing before I did this noise, how much information does that tell you that there'll be a crossing afterwards? Noise sensitivity means basically there's no information being transferred. And so that's what the question of noise sensitivity turns out to be in here. And the theorem concerning noise sensitivity was proven by Benjamini, Kalai, and Schramm that the percolation crossings are noise sensitive. So that if you have a crossing initially and you do this very small perturbation, you get no information whatsoever whether there'll be a crossing after the perturbation. So we call this noise sensitive. It's sensitive to a small amount of noise. So now this is if epsilon is completely fixed. The theorem, the statement is for every fixed epsilon, these become asymptotically uncorrelated. Now what's clear is epsilon gets smaller, the perturbation is closer to the original configuration, and so it's going to be harder for things to become independent. But still we can ask, what would happen if we let this epsilon not be fixed but go to 0 with r at some rate? Now, of course, if epsilon r decreases to 0 too quickly, you'll never get the independence of the crossing before and after. If epsilon's too small, the perturbation won't change anything. But one can still ask if it can go to 0 and what kind of rate. And in the initial paper where they proved noise sensitivity, they proved something stronger. They said we can even let the epsilon r go to 0 as long as it doesn't go too quickly. It has to be bigger than or equal to some specified sufficiently large constant divided by log r. So as long as it doesn't go quicker than 1 over log r, essentially, you still get this asymptotic independence of the percolation from before and after. And the next question one can ask is, what happens if the amount of noise, so this just says you can go logarithmically, but one can ask, can you send epsilon to r to go to 0 even quicker, like an inverse power? So what happens if the amount of noise, epsilon r, decreases to 0 as a power, or an inverse power of r, like 1 over r to the 1/2? Could you still have these things being asymptotically uncorrelated? Okay, so that we'll get this will be the motivating question, which we'll come back to in a few minutes. So now I'm going to introduce a couple other concepts that arise in Boolean functions and arises in this area that turns out to be very key to the study of all these things. And this key player is two things, which is called pivotality and influences. So now we go back to the general context of a Boolean function, and I want to talk about the idea that a particular bit I, so I is going to be 1 over a bit, the 5th bit or the 10th bit. I want to talk about the ith bit being pivotal. And so for a Boolean function Boolean function f, the event that I is pivotal, this is defined as follows. It's the event, and this turns out to be an event which is measurable with respect to the other variables. It's the event that if you were to change the ith bit, the outcome of the function would change. So in other words, take a realization and look at if f is 1 or minus 1. Now go to the ith bit and change it. Maybe f changed, maybe f didn't change. If f changed, then I say I was pivotal. Basically, it's pivotal for the event whether f is going to be plus or minus 1. So that's the notion of pivotal. And the notion of influence, the influence of the ith bit, which we denote I sub I of f. The big I is for influence. The little I is that we're talking about the ith bit. In f's our Boolean function, the influence of the ith bit is exactly the probability that I is pivotal. It's the probability that this occurs, that this particular ith bit is turned out to be very important in this realization, that by changing it, you change the outcome f. So let me go back to our 3 Boolean functions, dictator, the parity function, the majority function, and just check what that is there, just so that the concept's clear. So for the simplest one, for the dictator function, fn of x1 through xn is just the first bit. Obviously, the first bit has influence 1 because it's always pivotal. If you change the first bit, the outcome always changes. And the other bits, of course, have influence 0 because those functions, of course, those variables don't even come into f. For the parity function, that's also very simple. All the variables have influence 1 because if you take any bit is always pivotal. If I change any bit, the function gets multiplied, will just change because you're taking a product of plus and minus 1s. So trivially, all the influences are 1. For the majority function, it's not slightly more interesting, although not so hard to see, that the influences, of course, the influence of all the variables are the same because all the variables are playing the same role. And the influences are 1 over n to the 1/2 approximately. And this is basically because if you look at the first bit, what does it mean for the first bit to be pivotal? When is it going to be the case that the first bit, by becoming, can change the outcome? The first bit can only change the outcome if there's a tie among all of the other bits. And if you have n minus other bits and you want a tie between plus and minus 1s, this is basically like a random walk being back at the origin at time n, and this decays like a constant over n to the 1/2 power. So in this case, all the influences are 1 over n to the 1/2. Let me mention, although it's not so related to the noise sensitivity, it's sort of an interesting theorem if you find the notion of influence interesting. So I want to mention an interesting theorem in the area. And the theorem is an answer to the following question. How small can all the influences be? Now, of course, if you take f to be the constant function, all the influences are 0. So this is uninteresting. So we have to avoid degenerate things. So let's stick to functions f where the probability that f is 1 is, say, somewhere between 1/4 and 3/4. So it's non-degenerate. And if we stick to such f, you can ask how small can you make the largest influence? Is there any guarantee that there'll be some variable of reasonably large influence? And if so, how large? So if we looked at the majority functions, the majority functions show that the maximum influence can be as small as 1 over n to the 1/2. And the question is, could it get even smaller than 1 over n to the 1/2? And the answer is, it turns out it can be a lot smaller than 1 over n to the 1/2 power. So here is a particular Boolean function. So if you take the n variables, x1 through xn, and we're going to partition it into disjoint blocks, first block, second block, third block, etc. And the length of each of these blocks is going to be a sub n, which is going to be log base 2 of n minus log base 2 log base 2 of n. If you define the Boolean, so we partition it that way, and then we say that the function f is 1 if at least one of these blocks is all 1. So if you can find one of these blocks that are all 1, the function is 1. If there's no such block, the function is minus 1. Okay, this is a Boolean function. It turns out it's non-degenerate. The probability that f is is 1 is somewhere between, well, a quarter, and it's between a quarter and 3/4. It's non-degenerate. So it's easy to check that the functions are non-degenerate, and it's also easy to check that these influences are log n over n. So these influences are much smaller than 1 over n to the 1/2. In the majority function, it's log n over n, which is much smaller. And it turns out there's a theorem by Kahn, Kalai, and Lineal that says this is the best possible. So if you take any non-degenerate Boolean function, you always can find at least one of the variables whose influence is at least a constant log n over n. So the answer to the question, how small can the influences be? They can get as small as log n over n, but they can't get any smaller.
Does Leibniz achieve the optimal constant?
What's that?
Does Leibniz achieve the optimal constant?
No.
I don't know. No, Jeffrey says no.
What does?
We don't know. Well, we don't know what the optimal constant is.
So there's a gap of 2 over log 2, I think.
What's that?
There's a gap of, I think, 2 over log 2. Or no, there's a gap.
We're doing this in the optimal constant.
A multiplicative gap of log 2 between what the best proofs give and what the
Uh-huh.
Leibniz gives.
Okay. Okay.
But the best example is something like tribes, huh?
The best example is tribes, sorry.
Okay. So we originally talked about noise sensitivity, and then we moved into influences. So what is the so I should say that. So this argument uses Fourier analysis and hypercontractivity of certain operators, the so-called Benami-Beckner gross inequality. But I'm not going to be going into this. Is more of an overview, but these are the types of things that come in. So why are the influences relevant to noise sensitivity? If you're only interested in noise sensitivity, why do you care about the influences? And one of the fundamental theorems in the area was originally done in the Benjamin Nikolai-Schramm paper, which says that if you take any sequence of Boolean functions and you look at the sum of the squared influences, you square the influences, sum them up. If this goes to 0, then the sequence is noise sensitive. So in this sense, the influences give you information on whether you're noise sensitive. So this condition is certainly not sufficient. Is certainly not necessary, because if you take the parity function is it's very noise sensitive, but it certainly doesn't satisfy that because all of the influences are 1, and so that sum is in fact n, which is going to infinity. So it's not necessary, but it turns out to be necessary for a very large class of functions. The condition is necessary for monotone functions. This means increasing. So Boolean functions monotone if whenever you change some of the bits from -1 to 1, the output of the function can only increase. And it turns out for these, this condition is necessary, and so this gives you a necessary and sufficient condition for noise sensitivity. If you take the majority functions, I told you that this was not noise sensitive. What happens when you plug this into the formula? So the influences was 1 over square root of n. You square it, you get 1 over n. You sum it, and you get 1. So it becomes that sum is of order 1 for the majority. So it just barely misses satisfying this condition. And it turns out that the majority function is an extremal sequence in many respects for Boolean functions. This theorem is also proved using Fourier analysis, hypercontractivity, an inequality or generalization of inequality due to Talleyrand. Okay, so this is, if we take this general theorem, okay, so now we want to get back to percolation crossings. So I told you percolation crossings are noise sensitive. So how do we get the noise sensitivity of percolation crossings from this? So I told you percolation crossings are noise sensitive, and although it was not done in this way in the original paper, I want to explain to you basically how it would follow from this theorem. So assuming this theorem, how do we get the noise sensitivity? We have to somehow compute the influences for the particular case of percolation. So at this point, we now have the event of you have a square, an r by r square. The event is whether there's a left to right black crossing, and I want to have some way of computing what the influence is. And the answer to this is going to bring us into what are called critical exponents in percolation. So let me describe what these are. So first of all, I only describe percolation on an r by r box, but normally we do actually do percolation on an infinite lattice. So imagine you do percolation on an infinite hexagonal lattice. Now, we've always been taking P as a half, the probability of a black, but you could take the probability of a black to be anything. So imagine you take the probability of a black to be P, and white 1 minus P independently, and I want to ask, is there an infinite black component? So I do this on entire infinite hexagonal lattice. Is there an infinite black component? And the answer is it depends upon P, and there's a critical value. And it was essentially shown in 1960 by Harris that when P is a half, there's no infinite black component. And it was proven 20 years later by Keston that if P is slightly bigger than a half, if P is bigger than a half, then in fact you suddenly get this infinite black component. And so we say the critical value for percolation is a half. And at this critical value of a half, there's no infinite component. OK, now we look at this picture. We look at our infinite lattice. P is a half. And I want to look at the event that there's an open path, a black path from the origin to distance r away. Since the probability of having an infinite black path is 0, we know that this probability goes to 0. And the question is, how fast does it go? And how fast this would go is answered by Lawler, Schramm, and Werner in 2002. It says the probability of this event decays like, alpha 1 of r is just the definition of this. It decays like r to the minus 5/48, essentially, plus little o of 1. Don't worry about that. So it decays like 1 over r to the 5/48. And we call 5/48 a critical exponent. So let me just mention that there's a critical value, which is P as a half is the so-called critical value. That determines if there's an infinite cluster. And there's this critical exponent, 5/48. There's a big difference between them. So people like to say that the 5/48 is universal, and they like to say the P as a half is not universal. What this means is if you, a half, it happened to be the right thing for this model, but if you changed the model a little bit and did something else, you could get a different critical value for P. However, if you took a different model and looked at the critical percolation in this, if you looked at the percolation picture at the new critical value and looked at this event again, it's believed that this should still decay like 1 over r to the 5/48. So 5/48 should be the number that comes up for all these models, but the 1/2 was very special to this, and that's why they call that universal. OK, now there's another critical exponent that's going to be relevant for the influences, and this is called the 4-arm exponent. So now I want to look at the following event, that from the origin, there's 2 black paths going out, 2 white paths going out, and in this clockwise order, black, white, black, white. Again, of course, this is even more unlikely than the other, so the probability of this will also go to 0. And the question is, how fast does it go? And Smirnov and Werner showed that the probability of this event decays like 1 over r to a different power, and this other power is 5/4. So we say that 5/4 is the critical exponent for the 4-arm events, because there's 4 arms in this picture. OK, now this is exactly the right picture to capture the notion of influence. So what is the probability of a hexagon being pivotal for percolation? So now we're back into this crossing picture. We're looking for a blue now path from left to right. And we want to know, when is it the case that a particular, forget the D here, that a particular hexagon X is pivotal? And so what has to happen if X is pivotal? It means if X is on, if it's blue, there's a left to right crossing. And if it's red, there's no crossing. Well, so if X is on, that means there has to be some blue crossing from left to right. And this blue crossing has to cross through X. If the blue crossing didn't cross through X, then by turning X off, you wouldn't have gotten rid of the blue crossing. So for X to be pivotal, this blue crossing has to go through X. And in addition, there has to be no path, blue path, from this part of the path to this part of the path. Because if there were a path going like this there, you could get from here to there avoiding X. And X would not be pivotal. So in order there to be no blue path from here to here, there has to be a red. Red is now the other color rather than black and white were blue and red. No, there has to be a red path going up there and a red path going down there. So that's what the picture is for to be pivotal. And of course, as long as you're not near the boundary, this is exactly what we had on the previous slide, the 4-arm exponent with these 4 arms going out. And so the probability of being pivotal is, as long as you're away from the boundary, it's at most, by the critical exponent on the previous slide, 1 over r to the 5/4. And this yields the sum of, and what does this do to the sum of the squared influences? Well, there are r squared many hexagons. Each of the influences 1 over r to the 5/4. I square the 1 over r to the 5/4. I get 1 over r to the 5/2. I get r squared times that, and that goes to 0. And so other than dealing with, you have to deal with the boundary. It's not very difficult. You have to deal with boundary issues, because this is really the appropriate picture if you're away from the boundary. But this basically tells you that the sum of the squared influence goes to 0, and you get noise sensitivity. OK, so now if we go to quantitative noise sensitivity, this is the question is, can you take the epsilon r's going to 0? So recall that Benjamin and Schramm, as I told you, said that percolation crossings decorrelate under noise even when the epsilon r's go to 0, as long as they don't go too quickly, if they're bigger than constant over log r for a sufficiently large constant c. And might we believe that percolation crossings can decorrelate? And when I use decorrelate can mean lots of things. It can mean decorrelate can mean partially independent or completely independent. For me, decorrelate means essentially completely independent, so that they become asymptotically independent. Not that they're just not completely correlated, but they're asymptotically independent. So might we believe that percolation crossings can decorrelate even if epsilon r is 1 over r to the alpha? And if so, what would be the largest alpha we could use? If we take alpha too big, the probability, the noise becomes so small that things won't change and you can't possibly decorrelate. And so this is a well-defined question: how big can you get the alpha? And basically, a lot of the talk will be trying to convince you or telling you what's known and how to get what the alpha is. OK, well now you know the alpha. So the heuristic is yes. I don't know. This is the answer. Maybe we'll see the heuristic on the next slide. So yes. We might believe that crossings decorrelate, and a guess that the largest alpha is 3/4. And what I want to do in the next slide is explain to you why you might believe the best exponent is 3/4. OK, so I just repeated that here, so we have it here, a heuristic for the noise sensitivity exponent for percolation. Might we believe that we decorrelate even if we go like 1 over power? Yes, and the largest alpha is 3/4. OK, so by the bottom of the slide, I hope to convince you heuristically that 3/4 is the answer. OK, so recall so we already said this before, the 4-arm exponent says that the probability of a hexagon being pivotal is about 1 over r to the 5/4. So that's the probability of a hexagon being pivotal. So the expected, if we look at now the total number of, that's the probability of one hexagon being pivotal. If we look at all the pivotals and look at the expected number of pivotals, what's the expected number of pivotals? Well, we have r squared many hexagons. Each is pivotal with about that probability. So the expected number of pivotal hexagons is about r to the 3/4, which is the 3/4 above. Therefore, imagine you now, the noise is epsilon r, the probability to which you're resampling is 1 over r to the alpha. What would be the expected number of pivotal hexagons that we resample? We have this random set of pivotals. What's the expected number that we resample? Well, it would be exactly the number of the expected number of pivotal hexagons times epsilon r. So this would be just r to the 3/4 minus epsilon. So if alpha is bigger than 3/4, then the expected number of pivotals that we resample is going to 0. So if alpha is bigger than 3/4, that means we don't resample. We don't actually resample a pivotal, and things don't change. Okay. Now you might argue right away on that. You hold it. You know, it's possible I don't have to touch a pivotal to change things. Maybe I change this one, which wasn't pivotal, and this one, which is pivotal. I change them both. Of course, I could change things. So it's certainly not the case. The fact I didn't hit pivotals says I don't change things, but it's a heuristic. And in fact, making this heuristic rigorous is actually quite easy. So this can be made rigorous easily in a 5-minute argument. If alpha is less than 3/4, then the number of pivotal hexagons that we resample is now r to the 3/4 minus alpha, which is now very big. So that means that we're very likely to hit a pivotal now. And if we hit a pivotal, well, things change and things should all get mixed up. You've lost all your information. So that's the heuristic of the 3/4. Now, this part is much, much harder to make rigorous. But it's a heuristic where the 3/4 come from. If you hit a pivotal, things should change, and then maybe everything got lost in the shuffle, and you have no information about what. And so what you knew originally about the picture that you had a crossing gives you no information afterwards. Okay, so that's okay. So that now explains the heuristic for 3/4. So now let me tell you two different approaches that we use to get partial results. The first one didn't give the 3/4, but it was the first argument that gave that allowed epsilon r to go like 1 over r to some power. Now this approach and then the approach I'm going to describe after, they're very different. They're also very different than the original Benjamini-Kalai-Schramm argument that said if the noise is bigger than constant over log r, things go to 0. So although I should say, and I'm going to be getting into I'll explain very simply some of the Fourier analysis later, all the three approaches use Fourier analysis, but beyond that common component, the arguments are quite different. And on this slide, I'm going to describe the second approach, which is very related to computer science, theoretical computer science, you could say. So now you have to sort of think like theoretical computer scientists, if you know how they think. So we have a Boolean function. I want to consider a randomized algorithm. So before reading the slide, let me tell you in words what you should imagine a randomized algorithm is. Let's say you have a Boolean function of n variables. And you know what the Boolean function is. Maybe it's a majority, maybe it's something else. And I ask you to compute f of x1 through xn. Well, you could do it. You know the function f. But unfortunately, you can't see the bits. x1 through xn are covered. You don't know what they are. So what you can do is you can ask for me some of the values of x1 through xn. You might say, Jeff, tell me what the third bit is, please. And then I say, oh, that was a 1. And then you look at that and say, oh, that's a 1. Then please tell me what the 10th bit is. And maybe I'll say, that's -1. And then depending on, as you get more and more information, you keep on asking about new bits. But each new bit you ask about, which bit you choose, will depend on what you've seen up until that point in time. And you want to, now at some point, presumably before you found out about every bit, you might say, don't tell me anything else. I already know what the outcome is. For example, in a percolation picture, if you already found out there was a left to right black crossing, even though you didn't know some of the other hexagons, you wouldn't need to get any more information. And what you want to do is you want to do this type of thing, ask me these questions, with trying to ask as few questions as possible. Okay, so now given that it should be easy to understand this, a randomized algorithm, A for f, examines the bits one by one, where the choice of the next bit examined may depend on the values of the bits examined so far. Now, it's also allowed to be random. Which bit you choose next is allowed to depend on what you've seen and some exterior randomness. It even the first bit is random. So the algorithm might pick a bit uniformly at random or according to some other distribution. That's allowed. And that's what we call a randomized algorithm. And the algorithm stops as soon as you know what the output of f is. And now, I said you want to ask as few questions as possible. And so this is one way of describing this is the following. When the game is over, and you know what the output f is, there's certain bits which you've asked me about. And we let J be this random set of bits, the random set of bits that are examined by the algorithm. And you define, so that's a random set. And I define the revealment of A to be the following. I call it delta sub A. It sort of represents the degree to which my algorithm A, I call it A, reveals the bits. What I can do is for every one of these n bits, I can say, what's the probability that that bit was ever looked at by this randomized algorithm? That's the probability that I is in j. So if you fix j is random, but if I fix a bit I can talk about the probability that I is in j. In other words, the probability that you asked what I is. And I want to take the maximum, the maximum over all the different bits. And that's called the revealment of the algorithm. And with ODED, one of the theorems we have is that if you have a sequence of that let fn be a sequence of Boolean functions with an being a randomized algorithm for fn. And the first theorem says if these algorithms are such that the revealments go to 0, so for very large n, for any fixed bit, it's very unlikely you'll ask what the value is, then it turns out the sequence is noise sensitive. I'll explain concretely how you do this in percolation. And this also turns out to give you a quantitative version, which says the following. If the revealments go down according to some inverse power of n, so if it's most c over n to the alpha for some alpha, then if you take any beta less than alpha over 2, then you end up getting the noise sensitivity you want, as long as the noise is 1, we take the noise to be 1 over n to the beta. So what we're asking is fn of x plus fn of x perturbed, the noise version, with this very small amount of noise, 1 over n to the beta? This thing says that these become asymptotically independent at least whenever beta is smaller than alpha over 2, if you have a bound on this on the revealment. Okay, so what does this give you for percolation? So I have to explain percolation, I have to tell you what this interface is. I also, unfortunately, have to change white to black and black to white now. So now we're going to look at left. Unfortunately, I got these pictures from someone else. I have no idea how to change the pictures. So rotating doesn't help either. Anyway, now we want to know, is there a left to right crossing or not? And this is a way, this is called the interface between the two. This is often, when you look at SLE 6 for critical percolation, there's a famous picture of ODED, and this is what is going to be described here. So here's how you determine if there's a left to right crossing of whites. I start a picture, this red path here, and I continue the path, always keeping whites on the right and reds on the left. So the path goes, blacks on the left. So here it comes this way to be white, then I want a black on the left, comes down here. This defines the path. This defines the path precisely. It comes around and goes around. It always keeps the whites on the right. Comes here, bounces, then it stays here, then it comes back here and goes up there. Okay, it keeps whites on the right, blacks on the left. Now this red path tells you if there's a left to right crossing, because start this path, it's going to be bouncing off this side a while and this side a while. Eventually it's going to hit the top or the left side. If it hits the top, that says there's no left to right crossing, because on the left side of this red path is this black vertical path that will stop the white path. Conversely, if this red path, the interface, hit the left side before the right side, you could look at exactly what's above the interface, and that would be your white path. So looking at this red path tells you that if there's a crossing. Okay, now the algorithm is the following. The algorithm starts here. Now you might not like this, because that means I always examine this bit with probability 1, so the revealment won't go to 0, but let's not worry about that. The algorithm simply asks about bits it needs in order to be defined. So it says, what are you? It's white. Now it goes this way, the path, and so it asks this bit, because this is the next one it needs to know. That's black. The path goes up here. Then it needs to ask this one. So basically, this path is going to be, in the end, asking these bits on the two sides of the path, but no others. So that's how the algorithm works. Now, if we take now let's ignore the boundary. This doesn't really, you have to modify this. I'm not going to explain how to modify it. But if I'll tell you why it works if you're away from the boundary. If you're in the middle of if you're in the middle here somewhere, and I ask, what's the probability that this particular hexagon is being looked at by the algorithm? That's what we need to know. What's the probability this hexagon is being looked at by the algorithm? Well, to be looked at, you're only looking at the ones that are adjacent to the interface. So what has to happen is, if you take a point in this interface, you'll see you have a black path to the boundary and a white path to the boundary. So a hexagon near the center of the picture is examined only if there is both a white and a black path coming out of it. That's a critical exponent that I have not described for you. That's called the 2-arm exponent. And that's also a critical exponent which is known, and it decays like 1 over r to the 1/4. So this says points not near the boundary, the probability of them being revealed is at most 1 over r to the 1/4. You can do some extra randomization to get rid of the problems on the boundary. So hence, and therefore, by the previous theorem, you end up getting decorrelation if epsilon r is larger, as long as epsilon r is larger than 1 over r to the 1/8. So it gives an it gives a proof that you can let the epsilon r decay as a power, of this power, and you can still get noise sensitivity, the decorrelation. But of course, the 1/8, this is a factor of 6 off from the 3/4 conjecture. Yeah.
Do you have an example of a nice monotone function that is noise sensitive but has no algorithm with low revealment?
Yeah. Do GNP at p is a half, and do clique containment at the right value of clique. 2 log. Ask if you have a 2 log n clique. It turns out it's noise sensitive and there's no algorithm.
It's not really.
No.
It's whatever it should be.
Yeah. It's about 2. Yeah. The size you have to choose the size to get it non-degenerate. It's about 2 log, and then it only becomes a non-degenerate function at certain values of n. But there is an example, and it's known that there's no algorithms. It's known. So that's the best example I know for the answer to your question. I can also say, you might say, oh, okay, you're off by a 6, but can you find a better algorithm? This is one algorithm, and the answer is maybe you could find better algorithms. In fact, we don't know if you can find better algorithms. It's an interesting question. But nonetheless, there are theorems that say maybe they're better algorithms, but they can't be that much better. And there are bounds on how good an algorithm can be. And it's known that you can't possibly get up to the 3/4 through this via this method. Okay, so now what time? Do you know what time I started? 10 more minutes. I have 10 more minutes. Okay, so so the way this is all done is the Fourier set up you have the following thing. If you take the set of functions, now that's 0, 1 to the n, it should be plus minus 1 to the n into r. If we look at all functions, not just Boolean, this is, of course, a 2 to the n dimensional vector space, because the domain has 2 to the n elements. And there's a very, very nice orthogonal basis for this vector space, which are these sets called chi sub s, where s is a subset of 1 through n. If s is the empty set, chi empty set is just taken to be the constant function 1. And otherwise, chi s, it's the following Bernoulli Boolean function, chi f x1 through xn, is you simply take the bits sitting inside of s and you multiply them. That's chi sub s. If you know about group theory, these are the characters for the group z mod 2 to the n, but you don't need to, in this context, everything can sort of stay combinatorial. You don't have to deal with that. Okay, so those are the characters. Now, those are our basis elements. They're orthogonal, and therefore, if I give you any function f, you can simply write it out in this orthogonal basis. I can sum it up over all s contained in 1 through n, f hat of s, chi of s. And f hat of s is called the Fourier coefficient of s. And what's elementary to check, very elementary to check, is that this correlation here, which is what we're interested in, that this is equal to, that this can be expressed in the following very simple way in terms of these Fourier coefficients. Now, since my f is mapping into plus or minus 1, it has L2 norm is 1. That means if I sum up the squares of these Fourier coefficients just by Pythagoras' theorem, they add up to 1. But what's interesting is but you end up getting that this correlation is given by the sum k equals 1 to the n, 1 minus epsilon to the k times this thing. Now, if I sum up f hat of s squared over all the s's, we get 1. But here I'm just going to sum them up over the s's of size k. And this is sort of, we call this the weight at size k. And in order for this to be small, I mean, epsilon's small, but if I take 1 minus epsilon to a big power, it becomes small. And so what you basically want, noise sensitivity, corresponds to the Fourier weights, these things here, being concentrated on large values of s. That most of the weight should be on large values of s. That's what this formula tells us. So let me give you an interesting relationship between the spectral sample and something else. So it's not necessary, but it's nice to have the following picture. There's something called the spectral sample. Given a Boolean function f, its spectral sample, which we call script s sub f, this is a random set. It's a random set of 1 through n, and it's defined distributionally as follows. The probability that this random set is equal to s is simply the Fourier coefficient of s squared. These all add up to 1, so this gives us a probability distribution on the subsets. And then, if in terms of this random set, you can rewrite this correlation, which you want to go to 0, very nicely in terms of this s sub f, that it's basically just the expected value of 1 minus epsilon raised to the size of this random set. And so noise sensitivity is basically equivalent to the cardinality of this set going off to infinity. Now, so to understand noise sensitivity, what one has to understand is the structure of the cardinality of this set. And this set is a very complicated random set, but this tells us that's what we want to understand. So quantitative noise sensitivity can be obtained by understanding the typical behavior of this random set. Now, what's not so hard to get a hold of is the expected value of that. But the hard thing is to show you that the expected value of this random variable is actually telling you the typical situation. So there turns out to be an interesting relation between, we have two different random sets for Boolean functions. We have the spectral sample, that's one random set, and we have the pivotal set. The pivotal set is the set of points which are pivotal for the Boolean function. That's another random set. And it turns out that there's a very interesting relationship between them. Now, they're not defined on the same space, so you can't ask if they're independent or not, but that you can ask how they're distributionally related, and there's some amazing things. The probability that a given bit belongs to these two random sets are the same. And therefore, the expected size of these two things turn out to be the same. And it also turns out these two random sets have the same two-dimensional marginals. Now, this turns out to be very useful because you can sometimes obtain weak results for the spectrum. What you can do, this tells you that second moment methods turn out to be very useful because if you apply second moment methods to this spectral set, you can instead transfer it over to the set of pivotal points, which turns out to be a little bit easier to handle. And this thing allows you to transform sort of second moment arguments, but unfortunately they don't have the same distributions. In general, it's just these two dimensionals, so this can't carry you all the way as you want. So what's happening with percolation? So the expected size of these two things, basically if you look at the slides I told you before and put them together, the total influence is r to the 3/4. But what you need to show is that's the typical behavior of the spectral set. And it is very long paper and acted by Garban, Patet, and Schramm. This is just a corollary of what they did. They did a lot, but just as one thing which is relevant to the talk, is the main point of the talk, is that the typical behavior of the spectral sample is r to the 3/4. So not only the mean, it's typical behavior. And this was a very difficult project. And the fact that this is the typical behavior, this in the end yields the conjectured noise sensitivity. So that's what you need to do. And so the point is, even though one is really only interested in the cardinality of this, their method here, you didn't just look at the cardinality, it looked at this random set as a random subset and try to analyze in some way. And it turned out that it has some relationships to fractal percolation, and they were able to get enough information on it to prove this result. Okay, skip that part. And, okay. Thank you.